Hello everyone. Today I will present our accepted paper named Cache First Then Recommend. It's end-to-end deep learning proactive content caching framework. This project actually is a joint collaboration between La Rochelle University and AUC. Okay, here's our agenda for today's presentation. First, we will talk about our motivation. We will first define our problem and introduce the limitation in the existing approaches. After that, we will take a quick look to our methodology, where we have two variants actually, two-stage caching paradigm and end-to-end caching paradigm. And we will talk about data preparation caching scheme. And finally, we will demonstrate our experiments. We will explore the used data set for benchmarking, implementation details, ablation studies, and finally we will benchmark our DLC framework against state-of-the-art techniques. Actually, regarding the problem definition, many internet services and applications have gradually migrated to mobile networks in the past few years. This contributes directly to sharp rise in mobile traffic. Due to this surge in mobile network traffic, enormous challenges have emerged for mobile networks and IoT applications. So content caching technologies aim to overcome such challenges by storing popular content users may request frequently at local base stations, servers, or mobile or edge devices. And these caching techniques actually try to solve the problems in the network traffic. For content caching, the main question is which object to cache or evac and when. Actually, current approach have several limitations. Actually, several state-of-the-art methods adapt to variants of reactive caching schemes like FIFO or LRU and least frequently used. All of these actually don't predict an item future probability, which typically degrades the performance of caching because there is no proactive here. Actually, recent caching schemes have incorporated proactive behavior in contrast to the aforementioned techniques that predicts content popularity trends. For example, collaborative filtering based caching algorithm model the interaction between user and item features and delivers this information to try to predict the future trends. And actually, significant improvement in collaborative filtering has been achieved by learning interaction using deep neural network, as a success of deep neural network in a lot of or a wide range of application, computer vision and NLP. So it also explored in the recommendation system here. However, due to the overall success of LSTM, one of the variants, well-known variants of deep learning, which is very powerful regarding the sequences, actually in NLP and computer vision, it was also utilized in the content caching schemes, but it suffers from high complexities. That's why it is not efficient for deployment on edge devices. And also learning from OBT propose a gradient posting decision trees, which is efficient in terms of time and complexity, but its performance is not very good compared to LSTM algorithms. That's why this motivates us to propose a new architecture which is tackling both direction, efficiency, and achieving our outperforming the existing state-of-the-art methods. Actually, our framework have two variants, two-stage paradigm and end-to-end paradigm, where both of them actually is performing better than the state-of-the-art algorithms, and the end-to-end caching paradigm is much better from the two-stage paradigm in terms of complexity and in the accuracy, as we will see in details in the next slides. Okay, actually, in general, the formulation of the content caching problem consists of splitting it into two main modules, or can be interpreted as that. First, recommendation system, then caching scheme. And actually, the recommendation system will generate the recommending matrix M, as you can see here in the blue. And this matrix is a square matrix. Its size is n multiplied by k. And actually, n is the number of users and k is number of items. And after generating m, we wanna cache actually this matrix in a more condensed or more efficient matrix to be stored on the device, which is the cached matrix H, and actually this matrix is smaller than M, where KH is a configurable parameter representing the number of top selected items. So we want to move from M to H, which is a cached matrix. And actually, to formulate the recommendation system, we can formulate it as arbitrary function f, where f is taking as an input is the interaction between the user and different items, which is a matrix M, and this function, arbitrary function, should predict M dash, which is the recommended matrix. And actually, if the function f could be interpreted as arbitrary deep learning architecture, where we are utilizing fully connected layers to model this actually function, and this function is responsible to capture 3 levels of correlation. The first level is intra-user correlation, the second one is intra-item correlation, and the third one is cross-correlation between user and item. So actually, the 3 correlation could be interpreted as a fully connected layers, as you can see on the figure on the right. And actually, following this formulation, we are interpreting this problem of recommendation as a classification problem, where we are asking or need the model to judge that the following, actually, whether this item user item pair interaction is may exist or not. That's it. So it's 0 or 1, so it's a binary classification problem. And actually, in inference time, the complexity of such system is n times k, because we have n user and k items, and we have to check all user item pairs. That's why it's n times k, which is not efficient enough actually in terms of the inference time and even the complexity. And that's why we are trying to propose an efficient paradigm, which is end-to-end caching paradigm. It's much better than the 2-stage paradigm, as we will see now. And actually, in this caching paradigm, the network architecture and training objective are totally different, and we are trying to tackle the main problem, which is caching, not recommendation. As you noticed in the previous paradigm, our main goal actually is recommendation, or the neural network, or the loss designed to tackle the binary classification loss to recommend first, then cache. And that's why we called our paper actually cache first, then recommend, because it's our main objective. That's why we are tailored a deep learning encoder actually to tackle the caching problem directly. And how we can do that? Actually, we are trying to tackle this research question, which is, can we design a framework that directly tackles the content caching problem rather than using an intermediate stage, which is a recommender system? And actually, to this end, we propose end-to-end framework, which is much better than the 2-stage paradigm, as I mentioned before. And actually, let's see the details. Here we are adapting or tailored the training objective of the deep neural network to be a conditional probability output to estimate whether this actually interaction may happen or not. So actually, based on that, the last fully connected layer dimension will not be 2 as previous, as it was a binary classification. No, it will be k. So actually, for each item k in our data set, as you can see in the equation here, we will generate a probability. As you can see in the above figure in blue, we are generating a probability distribution conditioned on the user. So given this user, what is the probability of the preferences of this user across all k items in our data set? That's why actually C here in this paradigm will be equal k, because we are generating distribution across the k item. In contrast, in the previous paradigm, which is 2-stage, we are using a recommendation system as an intermediate stage. That's why k here is 2, because we are tackling a binary classification problem, which is totally different training objective. And actually, designing this new training objective is enabling us to directly tackling the caching problem, which is the main focus. That's why the accuracy increased a lot actually in comparison to the 2-stage paradigm. And actually, in another advantage of this paradigm is that the complexity is reduced. As you can see here now, the complexity in the inference time is just n. We are run or infer the network n times, which means that n, recall that n is a number of users. That's why for each user we are enter its preferences or its information, and we are getting a full distribution across k items. That's why we don't need to run it n times k, because for each n user we get the result for the whole k items, which is efficient in the testing time actually. A very key important aspect here is the data preparation. We need to create or following a windowing strategy. As you can see here, we have windows in green. The window size is a configurable parameter. It's easy, and actually our caching module adapts one of the shelf caching techniques. Let's say FIFO is the first window size because we didn't train our deep learning framework yet, so we don't have any. It's randomly initialized. We can't rely on it in the first interval. That's why we are adopt one of the off-the-shelf caching techniques, and after that we are try to create our training data, which will be used in the next stage. Actually, that's why, as you can see in the blue, we are creating our training data, and after that we are using the whole windows for testing and etc. With the time we are collecting more training data, as you can see in the second row. So now we have two window sizes as training data and the rest as testing and etc. And actually as the training size is increasing, the performance is increasing a lot. So we are starting at the beginning with not perfect result, and it increased with the time actually. And this is for the two-stage paradigm, while in the end-to-end paradigm there are a critical difference between both of them actually. That's why we need to follow a different data preparation technique. As you can see here, we have to split the training window size into input and ground truths to avoid trivial solution or data leakage of the network. And finally, after proposing two variants of our neural network paradigm, actually we have a content caching scheme, and actually we have three variants of this content caching scheme. The best one is the hybrid, and we will see how and why. First one is a centralized scheme. The centralized scheme actually ranks the item based on their frequency, and we need to pick the top k item for the all users actually. That's why it's called centralized, because all users we are getting top k for all of them. And actually per user is in contrast. For each user we have top k. That's why, as you can see on the right, the size is large. Instead of one top k, it's number of user top k, because for each user we are getting its preferences. And actually, as it's very intuitive, it's very complex. That's why we have this hybrid caching scheme, which is a compromise between both techniques, the centralized and distributed or per user one, where we are defining a hyperparameter which is called L. L is grouping technique for group. It's group each L users in one group, and we will pick enter each group. We will follow the centralized. So for each group we will get only top k for the whole groups. That's why at the end we will have L top k, and this technique actually solves the trade-off. And actually for the dataset we are following the MovieLens dataset, which have some challenges. Please refer to the paper for more details. And actually regarding our implementation details, all the models are trained 50 epochs from scratch, and actually we are using PyTorch as the deep learning framework, and we are using only one GPU, GTX 1080. And for ablation studies, we have conducted actually 4 ablation studies. First one is studying the effect of varying the rating threshold. As you can see here, while we are increasing the threshold, we have a better performance. And the second ablation is studies effect of varying number of groups L, and as it's intuitive, as we are increasing also the groups, we have a better accuracy. And the third one is the window size, and also it's very intuitively, as we increase the window size, we have a better accuracy. And the final one is ablation between or comparison between the two variants, the two stage and end to end. As you can see here at the bottom of the table, all on the different window sizes, end to end is achieving a better state of the art performance compared to the two stage scheme. And finally, we are benchmarking against the state of the art, and as you can see here, we are achieving the best results, as you can see on the figure or in the table, except of course the FOO algorithm, which is acting as or mimicking the optimal case. I hope our presentation was beneficial for you, and our ideas and hypotheses are inspiring for you. Thank you very much.